What we're going to look at in this video is we're going to look at one of the key things you have to be able to do with circles, and that's calculating the tangent to a circle. Now, if you'll remember in the previous set of videos, we're looking at points where a line can intersect the circle, and we came up with three sets of possibilities. One was where the line cut through the circle and we had 2 points of intersection. The second was when it touched at one point and we had a tangent to the circle. And the third was no touching, so it was just a line in outer space around the circle. What we're going to look at is the second scenario here. We're going to look at calculating the tangent to a circle where it touches the circle at only 1 point. This is a key skill you have to develop. Now, this may seem like a lot of jargon to throw at you in one go, but actually it's quite straightforward to be able to do. Imagine we've got a setup like this. So I've got a circle here, centre C at x, y, and I've got a straight line here touching it once at the point AB. Now this line here, because it only touches once, this is a tangent to our circle. Imagine we want to get the equation of that line. Well, there's a set of steps you should follow every single time, and if you do, you'll be able to get it no matter what. So step one, calculate the gradient from the centre to the point of intersection. So that's the gradient from this point to this point here. And again, we simply use the standard gradient formula we remember from back in National 5. The gradient was y1 minus y2 over x1 minus x2. Stick to that formula for the gradient and you'll be fine. Second thing is we then use m1 times m2 equals -1 to get the gradient of the tangent. Think back to unit 1 when we did this. Perpendicular lines multiplying the gradients together, we get -1. This then gives me the gradient of the tangent. Remember that if you've got a line touching the circle at any point, any tangent to a circle, it is always perpendicular to the radius of the circle. So it's always perpendicular to the line from the centre of the circle out to that point where it touches. So that's why we can use this property here. Once we've got that, we have the gradient of the tangent. We've got a point of intersection, so AB, which we'll use from the point where it touches. We can then plug it into the y minus b equals m bracket x minus a formula, and we get our equation of our straight line. Now, you can leave this in any of the formats that you want. So for example, you could have it as y equals mx plus c, or you could have it as the general equation of a straight line. So your ay plus bx plus c equals 0. Depending on the scenario, there's usually one that's better than the other to use. If it asks you for it though, just make sure it's in one of the right formats. So I'm going to give you a couple of examples of this. First example, imagine I tell you the point P at 4, 3 lies on the circle. That circle has a centre C at -2, -1. I want to find the equation of the tangent at P. So again, this is the kind of thing, you've got a circle there, got a straight line that touches there at the point P, and there's the centre of our circle C. Again, it's the same set of steps. Step 1, we get the gradient here. Step 2, we use our perpendicular properties of gradients, and then step 3, we get our equation. So step 1, we want the gradient from C to P. So again, y2 minus y1 over x2 minus x1. Let's do 3, take away -1, over 4, take away -2. 3 minus -1, same as 3 plus 1, which is 4. 4 minus -2, same as 4 plus 2, which is 6. Simplify that, and what you end up getting is that's equal to 2/3. So that's the gradient of our centre C to P. We then use the fact that m1 times m2 is equal to -1 to get the gradient of the tangent itself. So if we set m1 equal to 2/3, what we know is that 2/3 times the gradient of our tangent m2 is equal to -1. Flip this over here, you get m2 is equal to -3 over 2. So there's the gradient of our tangent. Now we have all the information we want, we can get the equation. So if we then go for step 3, which is that, we know we're going to use the point P at 4, 3 for our A and B. We can then plug all the data in. So we get y minus 3 equals -3 over 2 bracket x minus 4. It's now just a case of mucking around with this, multiplying out and simplifying it down. Now, key thing to remember, this is a fraction, get rid of it. I don't like fractions in this. Get rid of it as we're working through, put it in that format. So multiply everything by 2, I get 2y, take away 6, equals, and then multiply at the bracket with a -3 on top, -3x plus 12. get it all onto the left-hand side, so it's the general equation of a straight line, and we get 2y plus 3x, got minus 6, take away 12, take away 18, equals 0. That there is the equation of the tangent at P. We've done all three steps, one after the other, and we've got the answer we want. And it's that simple. Gradient, perpendicular gradient property, get our equation. So a second example for you here now. Imagine I've got a circle with the equation x plus 5 squared plus y minus 4 squared equals 40. First part, I want to prove the point B at 1, 6 lies in the circumference of the circle. Then I want to find the equation of the tangent at the point B. So for part A, I know if it lies in the circumference, if I substitute it into here, I'll get 40. So let's substitute it in and see. So I get 1 plus 5 squared plus the 6 minus 4 squared. What that equals is 1 plus 5 is 6, so I get 6 squared plus 2 squared. 6 6s are 36, plus 2 is 4, so that's 40. So there we go, it's equal to this hand side of the equation, B's on the circle. So what I can now do is then go about finding the equation of the tangent at that point B. And to do this, it's the same set of steps as we've done in the previous example and we described a couple of slides ago. First, we start by finding the gradient from the centre to the point. We then use the perpendicular property m1 times m2 equals -1 to get the gradient of the tangent. Then we substitute in the information, the gradient and the point, which will be B in this case, into the equation of a straight line and simplify it down. So first thing I should really do is look at the equation of the circle here and read off the centre, which we'll call C. Now remember, x minus a, y minus b, where a and b are the centre. That tells me then that the x part of the centre is -5, the y part is 4. So there you go, there's the centre of my circle given in this equation. I then want to do the gradient of b to c. Again, same simple formula, y1 minus y2 over x1 minus x2. So I do 6 take away 4 over 1 take away -5. 6 minus 4 is 2, 1 minus minus 5, 1 plus 5, which is 6. My gradient in this case is 1/3. Then I use the m1 times m2 equals -1 part. I know that one of the gradients, m1, is given by this, so what I know is that 1/3 times m2 equals -1. From that, I can read off the fact that m2, my gradient of my perpendicular line, i.e. my tangent at B, is given by -3. I've now got all the information I need, I've got my gradient, I've got my point B from up here, I can substitute them in. So I can say that y minus 6 equals -3 bracket x minus 1. Then it's just a case of multiplying out and simplifying. Y minus 6 equals -3x plus 3, and the two formats I can leave it in, so I can either leave it in the format y equals -3x plus 9, or general equation of a straight line format, y plus 3x, then got -6 minus 3, take away 9, equals 0. Again, either's irrelevant. There's some that are preferred, but depending on the next part of the question that you're going to go on to do, if you have to use them, one of these is probably better. It's the same set of steps every single time you want to find the equation of a tangent. First, you find the gradient from the centre to the point where it meets. Use the m1 times m2 equals -1 property of perpendicular lines to get the gradient of the tangent. Then substitute in the information using the point of contact as well. Same set of steps every single time. Follow them, get them. You'll get no problems with these types of questions.